Okay, so last lecture we did the statics of rigid bodies. We figured out we saw that we could choose a nice natural coordinates for a rigid body. It was in the form of the position of the center of mass and three angles, which we call theta, psi, and psi. These are the Euler angles which specify the body frame. So by that we means, let's say this is the EI prime is this notation, and RJI is some rotation matrix which we defined last time, and it's given in terms of these guys. Okay, so in these coordinates, the kinetic energy of the rigid body is center of mass part of the story plus omega transpose dot I omega, where this was the moment of inertia tensor, and this was the angular velocity of the rigid body. Okay. And there's also another notation for this quantity, which is called dyadics. I mean, it's just some name. This is called. This is notation.
Hello.
Yeah. Go ahead. Yes. Yes. Yes, Bera.
Sir, the video froze for a little.
That could be my. That could be just my internet connection is sometimes not so great, but it's okay now.
Yes, sir, it's okay. Yeah.
Okay, good. Or it could be your side as well. Okay, so we don't know. So, okay, good. So, okay, so and so omega we can also define it through the body frame. Okay, so this is what we mean by omega. So and so we also I need these formulas. So exercise was that, which I gave last time, was omega 1 plus some phi dot sine psi sine theta sine psi minus theta dot cos psi. Omega 2 is phi dot sine theta cos psi plus or minus, okay, this is plus and this is minus, theta dot sine psi. And omega 3 Oops. Okay, so this is just a recap from last lecture, and so are there any questions and comments? Okay, of yourself. None. So now we would like to ask, what is the angular momentum? But of course, it depends on choice of axis. And what we will do is we will choose to compute with the center of mass, asteroid, basically in the frame which or in the body frame. Okay, so let's go back to first principles and go back to, and so remember we had coordinates y a with masses m a, and a went from 1 to n, and so what we will do is we'll just define the angular momentum, okay, L or N, now L, we'll define it to be the sum of the angular moment of these individual masses, that is just r cross p, right? So we just do this N. Okay, so and what is ya dot? It's just omega cross ya. That is because in the center of mass frame, the y, the coefficient, so remember this. Okay, so these guys are fixed numbers, so when you take derivatives, the only contribution comes from taking the derivative on this guy. So this is what we can plug it into this, and we get, it implies L is equal to summation A M A Y A cross omega cross Y A. Okay, so okay, so now we have to use the cross product identity, and which I will do. But I need to use an exercise so that L equal, rather Li. So what we are going to say is L equal to some Li Ei some other I. Okay, and then okay, so basically you have to massage things around here, and do this calculation. And what I'm claiming here is that all the A dependence can be absorbed again in terms of the moment of inertial tensor. Okay, so this is the only thing you need to check here. So let's take this formula and ask the following thing. So some remarks. Okay, first remark is that L and omega need not be parallel to each other. Okay, easy way to do this. Let's just consider L1. What would L1 be? I11 omega 1 plus I12 omega 2 plus I13 omega 3, so on and so forth. And you can see that so let's consider a simple case, and so on and so forth. There are three more things. Suppose omega 1 is not 0, but and omega 2 and omega 3 are 0, then we can quickly write out various things. L1 will be just I11 omega 1, and so that means it's just omega is along the x1 prime, e1 prime is along e1 prime. So if L were also that way, L2 and L3 should be 0, but we see that L3 will be, rather L2 will be we'll have one term which is I21 or I12 omega 1, and this also need not. So I21 need not be 0, right? We saw it's a symmetric. So L3 will have one more term, which is I31 times omega 1. So you can see that unless I21 and I31 are vanishing, which need not be the case, L and omega need not be there. Is this point clear? Okay. Any okay, very good. Thank you. So the second remark is that which I mentioned last lecture, Ij is symmetric. Okay. So what we can do is we can choose that exists special body frame where Iij are diagonal. Okay, and so we'll give a name for that. Okay, frame. It could also be frames sometimes. Okay, are called the principal axis. Okay. And how do we see how such a frame is available? So that's very easy. So we saw that Iij is a constant matrix. So let's just go and call I prime to be some. Okay, so the theorem we know is that there exists an special orthogonal matrix which will diagonalize that I prime is diagonal. Okay, and so geometric, what does this mean? It just says that there exists so EI, let's call this double prime, will be just some, maybe something like this. R or R transpose, I'm slightly confused, but okay. So this R here is just this R. So R is the orthogonal matrix, special orthogonal matrix that diagonalizes Okay, that's all. And and we know this for symmetric matrices, this can happen. Okay, for any symmetric, nothing special about the moment of inertia. Okay, so the picture one has is the following: is that suppose we had like this E1 prime, E2 prime, E3 prime. These are not principal axes, but we could always find some new set of axes. Okay, and so it might be useful to work in with. Generally, we tend to work in so useful and simplifies also to choose the principal axis as the solution. Okay, so in particular, what does that mean? It simplifies things. For instance, T. Okay, just the rotational part of it. I'm throwing away the center of mass part. So it's be something very, very simple. I1 square plus I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square. Okay, where I1, I2, I3 are the diagonal entries. That's the moment of inertia tensor. Okay, so now we can we have expressions for omega 1, etc. So let's just write out what T rotational is. I1 into phi dot sin theta sin psi plus theta dot cos psi whole square plus half I2 omega 2 square. So I should phi dot sin theta cos psi minus theta dot sin psi whole square plus I3 phi dot cos theta plus psi. Okay, so now so we would like to find out, for instance, what the various what are the canonically momenta canonically conjugate to pi psi theta. Okay? So let us, for instance, look at dt by d psi dot. And you see here psi dot appears only here, so we get equal to I3 into phi dot cos phi cos theta, sorry, psi. And this is just I3 omega. Okay. So while we are at it, let's also try to write the equations of motion for the psi variable. So dt by d psi is slightly messier because psi appears where does it appear? Let's underline all those places. Psi comes here, here. Okay. So anywhere else? No. So actually, yeah. So you can't simplify things further. If I1 were equal to I2, then you could use some identities, etc. But right now we cannot do any simplification. So we just do the stupid thing, which is to take the derivative with respect to various things. Okay. So so it will be I1 so it's slightly messy. So exercise. So I don't want to do it. You can just do it and put all those terms in, and what you will get is something interesting, and that is I1 minus I2 omega 1. Okay, so the Euler-Lagrange equation of motion for a free rigid body okay Euler-Lagrange equation of motion for a free rigid body with respect to this one of the Euler-Lagrange, there are three, there will be two more, will be just d by dt. Okay, so if you work this out, so what do we get from this? You get d by dt I3 omega 3 equal to I1 minus I2 omega 1 omega 2. Okay, now you might ask how do we get the other equations, and we can go ahead and do the equations of phi. We are taking derivatives with respect to phi and theta, but there is something very cute about what we have here. Okay, so here what we are seeing is that this at least one of these Euler-Lagrange equations has just come. We are able to rewrite it in terms of the diagonal components of I and the omegas. Okay, so we can easily guess, just doing this, 3, 1, 2, 3, 1. So just do these replacements. Replace 3 with 1, 1 with 2, and 2 with 3. We'll get the other equation. So for instance, let's do that. d by dt of 3 becomes 1, and then 1 becomes 2, I2 minus 2 becomes 3, omega 2, omega 2. Do it one more time now. d by dt of I2 omega 2 should become, 1 became 2, it will become 3. Okay, so just using symmetry of the way, there's nothing special about 1, 2, and 3. So these Euler's equations are free rigid body. Okay. Is the logic clear? What I have done?
Yes, sir.
Okay, so little bit of work was needed to do. So I took the easiest one, which can be expressed in this fashion. And then once you have it, you can just forget everything. Okay, of course we need, if you want to do more with it, you need the explicit equations, but this is kind of cute that it comes out this way. Okay, it's kind of nice. So something which we know from, we can prove this, but I don't want to prove it. We know that for a free rigid body, angular momentum is conserved. There are no torques. Okay, so usually we write it as dl by dt equal to some torque, that is right, torque, which is 0 for a field. Okay, so but what is dl by dt? Now we can just write L as Li di hat. Okay, and so then dl by dt would be this is the statement. Okay, so exercises, check this. Okay, check this. Does this follow? It should, I think. Hmm? The answer is of course yes. Okay, so these equations. So you just look at it a little bit. So what do we have? So come back here. So yeah, let's pick this. What is I3 omega 3? Remember, these are the principal axes. So what is I3 omega 3? Li.
Okay.
Okay. Similarly, this is L1. This is equal to. Okay. So we just have to go back here and work through this. Just show that this. So you can see that this is quadratic. This has 1 omega, and Li is also has one more omega with an I omega kind of thing. So this is equal to I omega I. You know, I don't write this because I want a summation over I. Okay, but you understand, right? So you see that this is quadratic. So this equation is nothing but conservation of the angular momentum. Okay, good. Any questions? So let's start doing some simple things. Okay, so we'll do a simple repetition. So we'll take free rigid body. Okay, and we'll be in the center of mass frame. That means origin is okay. And so let's assume some symmetry. That is I1 is equal to I2, but that's not equal to I2. Okay, so we get. So now what we can do is we can look at if let's look at d I3 omega 3 by dt. This was equal to I1 minus I2 omega 1 omega. But what's happening here? I1 is equal to I2, so this becomes 0. Implies that L3 So now we can look at the other two equations and ask what does it mean. Okay, and also it also implies omega 3 is also constant because I3 is unknown. Okay, so let's look at the other two equations. So that is d I1 omega 1 by dt equal to I1 minus I3 I2 Okay, so let me just do some small changes. So let's just say since I2 is equal to I1, let me replace wherever I see I1, I2, I put I1. Sorry, I have to. Okay, so we get something like this. So we can simplify things. So d omega 1 by dt equal to I1 minus I3 by I1 omega, and remember omega 3 is also a constant, so we can just write these things. All these are constants, omega 2, and d omega 2 by dt is equal to minus of the same thing, right? I mean the minus and I put because what we have here is I3 minus I1. Okay, so that's what we get. And let me make an assumption. Let me assume something about I3. So what we can do here is, so these are all numbers, and so what we can see is, so let's call, let omega be equal to I1 minus I3 okay, and let me put a magnitude here because I3 might be greater than I1, I2 might be greater than this thing, so we don't know that, so let's just put it like this. And then we can take, we can do the following thing. So we can just differentiate this one more time with respect to time. And then what we will get is that we'll get this equation. D square omega 1 by dt square is minus omega square omega. Similarly, d square omega 2 by dt square will be minus omega square omega. So these two are equations which we know. So what this says is that omega 1 is equal to a sine omega, some constants depending on the initial conditions, plus b sine cosine omega t. And omega 2, we can actually go ahead and use this form from this. It's just taking, rather this one. And omega 2 is just taking derivative of this. So let's do that. Is equal to d 1 by omega maybe. Okay, that's the overall sign. So let me just do this and then I'll fix it. So this will become okay. So up to a sign. Do you understand why I'm saying that? Okay. So what is appearing here is omega square. So we could fix things by saying omega is 2 minus omega. I don't know. Okay, up to a sign. Do you understand why I'm saying up to a sign? Okay, so if omega is defined to be I1 minus I3 by, what is it, I1 is greater than 0, okay, then this sign is okay. However, if omega, with same definition, I1 minus I3 is less than 0, then you need a sign. So what I will put here, maybe I should do that. I can just do that. Sine of I1 minus I3.
Sir, up till this point we were using modulus of
Yeah.
omega, right?
Yeah. Omega is a positive number. I want it that way. So that's what I'm going to do. Sine of I1 minus I3. Okay? That will take care of this. So we get, so now we can understand what is going on here. So picture is always better. So what we have is that, let's say this is the 3 direction of omega, and omega, so what we see is that this omega vector, let's draw 1 and 2 also. Okay, so these are the directions, and then we have omega, which is just some vector like this. Okay. So how does it, so first thing we know is omega 3 doesn't change, but what you can see here if you look carefully is that omega 1 square plus omega 2 square, where is that solution that we wrote? Yeah. So you can check that omega 1 square plus is a constant, it's just a square plus b square, which is determined by the initial condition. So what is happening is the omega vector recesses. So in other words, it goes around. The tip of this will be a circle vector, recesses about the E3 prime axis with frequency, with angular frequency, of course. Okay, so is this clear? That's what is happening. That's what this is saying. You can see, for instance, let's say put t equal to 0 in this expression. Can you see my, oh, you can't see my mouse, right? So 1 second. Now can you see?
Yes, sir.
Okay, good. Okay. So what is happening is that, yeah, let's go back here. So at t equal to 0, omega 1 is 0. T equal to 0, omega 1 is b, and omega 2 is, let's choose the plus sign case. Omega 2 is a. Okay? So it will be in some direction. Or let's even do something simpler. Let's work on a situation where a is 0. Sorry, b is at t equal to 0, b is 0. So then at t equal to 0, it's entirely omega 2 only, which is non-zero. And then if you wait for, half cycle of this omega, then what you will see is that omega 1 will be 0, non-zero, and omega 2 will be 0. So it is the usual precession, but this is the precession of the angular velocity. Okay, the vector doesn't change. The magnitude of the vector doesn't change, but so that is this picture which I have. Is this clear?
Yes, I got it.
Okay, good. Okay, so now that was our first simple example. Now we will do a fairly interesting example. So our next example, which we will start. Okay, is the following. Okay. So
Sir, this scenario looks like that top, like that.
this is not here. I mean, but top is usually in the presence of gravity, which is what we're going to do now. We don't have any external torque forces, nothing. It's just a free. That's all. Okay, so yeah, we will get on to this. There is following. It's something called a symmetric torque. Okay, so symmetric means, let's say I1 is equal to I2. We already considered that. It is not equal to I3. I think this is what you are referring to. And there's also nomenclature. Heavy means that I3 is much, much greater than I1, which is equal to I2. Okay? So this could have been applied for a free top also, but the top is under the action of gravity. Okay, so again we draw a picture. Something like this. The center of mass will be somewhere here. Okay, but let's say that there's a point where, so we'll have one frame which is set here. Or let me use a different color. Go back to it. Okay, so this is the center of mass, and so let's say that there is this vector H, okay, which connects up these two different things, and G is acting in this direction. Okay, so here, the thing here is that this is a different origin. Origin is no longer. So origin is not the center of mass. It need not even be a point on that thing. Okay. So now we need to account for this. So moment of inertia. So I'll do this first. Moment of inertia depends on okay, so we'll do a small exercise before we start this problem. So the exercise is a very simple one. How does the moment of inertia tensor, how does the moment of inertia tensor change under change of origin? Okay, so first let us just go back to the definition of this and do it in the continuum version. Okay, so this is with respect to one vector R. Let's say we have some R tilde, right? which is just shifted with respect to r, with a as a constant vector. So we can just define I tilde, ij, exactly like we would do here, except it would be integral I tilde or I prime, okay, it will be integral over v d cubed r tilde rho of at location r tilde. Okay, I won't put the argument properly. Okay, so what is r tilde square? It's just r plus a dot r plus a. So if you expand this, you get r square plus 2a dot r plus a square. Okay, so you go ahead and so we can, so if you look at this term, so and here it is easy, xi tilde, xi tilde is nothing but xi plus ai. Okay, so I tilde ij will have one term which is iij plus term linear in A, right? Okay, which I'm not writing, but I'll write the last term. I'll write integral d cubed r rho of r times quadratic in A. That would be just. Okay, but what is this? You can see A is some constant vector, so I can pull it out the integral. What is this?
Mass.
Mass. Okay, so now we'll make a claim. Okay, it's the following. The order A term is 0 if, okay, iij is computed with respect to with the center of mass of solid. If it is some other point, you can't. If you go back and look at last lecture, we had this identity. It's really this. So what does it mean? If it's a linear term in AI, okay, then the other term should be, so the coordinates will be yi, right? So it will be term which will have yi, and ai is some constant vector. So why do you, so this is what will happen. So it's really a consequence of this. So we get a nice cool formula. Mass times maybe we should remind ourselves that this is computed with respect to center of mass. Okay, so we can do several examples, but I will not do that. But I want to remind you of results you might. One of them is called some parallel axis theorem. Okay, what does it say? Suppose you. Okay, so the other one is called perpendicular axis theorem. Do people remember these things? Okay.
Yes, sir.
Okay, so perpendicular axis theorem is actually is not very. It's only true for holds only for what are called planar objects. Okay. So what it says something like, if you have some planar object, and let's say this is in the 1-2 plane, it has something to do with saying that I33 equal to, let's say I22 plus I11, if these are the principal axes, whatever. Okay. So, but parallel axis theorem is that is a little bit better. I mean, in the sense that it holds in more generality. So if you have some axis one and you shift by this thing, so this will be shifted by some vector A. So you go back and look it up. Okay. So but you can get the answer from precisely from using this formula. You can do that. I don't think you can prove perpendicular axis. Well, you can. I mean, perpendicular axis theorem is something which you can check easily. So it's only for planar objects. Okay. So I stop here, and next lecture we'll do the dynamics of this heavy symmetric top, and you will be amazed at how rich structure underlies these equations and its solutions. So this is something which we will work through in the next lecture. So I'll pause here. I'm done with my lecture for questions. No questions? I have a question. I mean, do you people vaguely recall parallel axis theorem, perpendicular axis theorem from? I remember from my high school.
Yes, sir.
Yeah. Okay. But at that time we don't appreciate it so much. We just remember it as we memorize things, but now we don't. Okay. So if there are no questions, I'll just stop the recording.